Okay, so since the lab really did not work the way that I thought it was going to work, I was like, okay, everybody seems to be getting really confused. So I thought this review video would be helpful for all this Q stuff, Q and delta E and all that. If we go back to the beginning of chapter 6.4, that was kind of on Friday where I reminded you of things that we've done in honors chemistry. So a substance's ability to change temperature is dependent on what we call its heat capacity. So if we are measuring energy, which is Q, and usually it's in the unit of joule, okay, the amount of joules that are going to change, either from being absorbed or being released, is dependent on the mass of the object in grams, the change in temperature, and then a unit that we call the specific heat, which is specific to every substance. And inside of this, okay, this is joules per grams times temperature. Okay, so the CP has all of that in there. So if you have a substance like water, okay, water is 4.18 joules per gram per degree Celsius. So that means every time you want 1 gram of water to change per degree Celsius, it's going to have to absorb 4.18 joules. And water has a very high specific heat. Most substances like metals are going to have a specific heat less than 1, which is the reason why they heat up and cool off so quickly. The first example that I showed you in class was on page 258. It's example 6.2. So it says that you find a penny in the snow. The snow is -8 degrees Celsius. And you keep it in your hand, which is 37 degrees Celsius. Okay, it says that the penny weighs 3.10 grams, and to assume that it is made of 100% copper. And copper has a specific heat of 0.385 joules per gram degree Celsius. Okay, so if we want to figure out how much energy did that penny absorb from your hand, then we want to plug it into this equation. Okay, so we know that it weighs 3.10. We know the change in temperature. It ended up 37 degrees. It started at 8, so this is really a plus. Okay, it started at -8, excuse me. And then the specific heat is 0.385 for every gram and degree Celsius. So really all we have to do for this question is multiply, and the answer is that it absorbed 53.7 joules of energy. Okay, so the penny is absorbing the energy, your hand is losing the energy. So at the same time as the penny is absorbing, okay, what we're really saying is that if the penny was, say, the system, okay, the system is absorbing 53.7 joules, okay, the surroundings are losing the exact same amount. Okay, so it's going from your hand into the penny. Okay, and that kind of leads us into the idea of like how a calorimeter works. So in the lab, okay, we had the calorimeter, which it was the coffee cups. Okay, and then you have the water, which is the surroundings, and inside the water you put a hot piece of metal. Okay, so we would call the metal the system, okay, because it started out with the high temperature. Okay, so when the two mix, the heat always transfers from the hot to the cold. So the metal's heat is going to transfer into the water. So we really have two Q values here. We've got one Q for how much energy the metal is losing, and then we have another Q for how much energy the water is gaining. So in the book, it writes it as positive Q for the system equals negative Q for the surroundings. Okay, but it can also be negative Q for the system equals positive Q for the surroundings. Okay, the negative and positive are just a directional change. So as long as like you can pick whichever side you want to be negative, you just have to make sure that you distribute the negative properly, because it's really all about perspective. Okay, are we talking about what's happening from the water's perspective? Because in that case, if you're putting hot metal in the water, it's going to be gaining energy, and that would be positive. Are you talking about energy from the metal's perspective? Because that would be negative because it's losing. Okay, as long as you keep your perspective consistent, you can call whichever side you want negative. So much like in your lab, if you have a situation like this where you take a cube of heated metal and you submerge it in water, Okay, you can find an unknown by setting up the fact that you understand that the Q from one is the Q for the other, but it's the opposite. Okay, so one gains, the other one loses. So this is really like saying the mass and the change in temperature and the specific heat of one substance is the negative, equal, and opposite of the other substance. Okay, so if we decide that we want the system to be the metal and the surroundings to be the water, okay, we need to plug in the mass, the change in temperature of the metal, and the specific heat of that metal. And on this side, plug in the mass, the change in temperature of the water, and the specific heat of water. So we've got 32.5. Okay, the change in temperature, it's asking for TF, so we don't know what the final temperature is, but it says they both end up at, oh, excuse me, the metal began at 45.8. Okay, and then the specific heat of aluminum is 0.903. On the other side, we have water, so we have 105.3 grams. And we don't know TF, but we know it started at 15.4. And then the specific heat of water is 4.18. Okay, so now it's all about algebra. Okay, you do have to remember to distribute the negative. Once you get everything worked out, we're going to end up with numbers on each side. So let me just pause here for a minute and calculate some of this. So first simplification, I took the 32.5 times 0.903, okay, and made that one number. On the other side, I did the same thing. So now the next step is going to be to distribute. So I'm going to distribute the 29.3 to both of these numbers, distribute the 440 to both of these. Okay, so when you distribute, you end up with two TF numbers and two numbers with no unit. So now you just have to combine like terms. So I will probably add both sides by 1341.91 and then add both sides with 440.15 TF. Okay, now it's starting to look like an easier question. So we have a number with TF, we've got no number, or a number with no unit, so if we want TF by itself, we need to simply divide. And the final answer is that they both end up at 17.3 degrees Celsius. Okay, let's try one more example of two that are coming to equilibrium. So this time we know starting temperature for both, final temperature. What we don't know is the mass of the copper block. So we've got Q system and negative Q surroundings. Okay, I'm going to stick with saying that this is the metal side and this is the water side. Okay, so we do not know the mass of the copper, but we do know that it changes from 65.4 to 24.2. So that is a change in temperature of 41.2. We know it's copper, so the specific heat is 0.385. On the other side, we have all of the negatives for water. So we've got 95.7 grams. Okay, we have a change in temperature that's much smaller, so 24.2 minus 22.7 is 1.5. Okay, and then water is 4.18. So this one's a lot easier because of the whole TF thing not being an issue. So we really just have to multiply and then we're going to divide. So I'm going to simplify. I'll get m times the number equals something. Give me 1 second. Oh, I see something that I missed. Okay, so one thing that I need to point out, because we have an issue with one side being positive and one side being negative. For the metal, because it was the final temperature was 24.2 and the initial temperature was 65, this is actually a negative change in temperature. Okay, which it matters because if you don't fix that now, you're going to end up getting a negative as your answer for mass. The value will be the same. It's just supposed to be positive, not negative. So again, it's just kind of tricky being careful with directions and stuff like that. So when we simplify, we get that the mass is multiplied by negative 15.9 and the other side is negative 600. To solve for mass, we simply divide. and the mass of copper was 37.7 grams.